Greetings. In this one, we're still working on alcohols, and it's our turn to draw alcohols that match whatever name they give us. So, the name that they give us for an alcohol always contains its primary, and they start us with a really simple one. Methanol is based on methane, which is a single carbon. Doesn't get much easier than that. And the OL ending instead of methane tells us it has a hydroxyl group. That's the functional group that makes it an alcohol. So, that's methanol, though of course it isn't complete until you've put the hydrogen fur all around it. There we go, methanol. Difficult to draw as a structural formula. You end up doing this. And this end of the line, because nothing is written for it, is understood to be the carbon. This end, which is labeled OH, is where the hydroxyl group is. So this one always feels weird to me because I always think this should mean two carbons, even though I know the rules perfectly well. That's what you'd do if you had to do a line structure for methanol, but for something this small, it's not much of a burden to draw the whole thing. Okay, propan-2-ol. Propane is familiar to us. That means three carbons in a chain. And the ol means attach a hydroxyl group, and methanol didn't need a number because I didn't have any choice. It had to go on the only carbon. This too is telling us attach your hydroxyl group to the second carbon. You can write it like this, or you can write OH in a vertical configuration, but either way, that's the structure. And once again, we buzz around and put hydrogens all around it. If you did this structurally, you'd have one carbon, two carbons, three carbons, and then hydroxyl group on the middle. And that dot should not be there, really. I put that in to remind you there's a carbon on the end, but in a real structure, you just have the lines. All right, complexity intensifies. Butane 1,2-diol. That E should not be there. I know I've seen that before. I've seen ethane diol too. Sometimes they leave the E on, which is not technically how the name is supposed to work, but it's not a deal breaker. We can do this. Butane has four carbons. 1, 2, 3, 4. Diol means there are two hydroxyl groups, and they are on the first and second carbons. One there. You can put them both on the same side realistically. From pair repulsion, I believe they would go opposite like this. And then, once again, turn your brain off and let muscle memory draw the hydrogens for you. And that's 110 butane 1,2-diol. Structural diagram would be 1, 2, 3, 4 carbons, and then let's go like this. 2 hydroxyl groups. 3-ethyl 4-methyl. Okay, this one has branches, more about them later. Focus on the primary. Octan-1-ol is octane, of course. So 1, 2, 3, 4, 5, 6, 7, 8. The first carbon gets the hydroxyl group. We always say it OH when we're talking about it, but if it's on this end, you'll often see people write HO because it is true. The oxygen is the one that would bond to the carbon, and then the hydrogen would be attached to that. So this is truer structurally, that the oxygen is closer in and the H is on the outside. So that's octan-1-ol. Then they say on the third carbon, attach an ethyl group. That's the third carbon. Ethyl groups have 2 carbons. And on the fourth carbon, attach a methyl group. I'm going to spare myself the hand cramping and not draw all the hydrogens around this. I trust you can handle that. It'll be 2, 2. Here there are 3 attachments, so just 1, CH2, CH3. This will be a 1 because there are 3 branches committed already. 3, 2, 2, 2, 3. And with the structural, you'd get the octanol would be 1, 2, 3, 4, 5, 6, 7, 8. Yeah, sorry. 1, 2, 3, 4, 5, 6, 7, 8. Okay, yeah, that's the octanol, and then we can have an OH coming off of that, and on to the third third carbon has an ethyl group coming off it, and the fourth carbon has the methyl group. And the horrendous finale. 2,4-dimethyl, that's branch, we'll deal with that later. Cyclopentanol. Okay, cyclopentane is 5 carbons in a ring. A pentagon, if you will. Not my best pentagon. Pentanol has a hydroxyl group on it, and they didn't give a number for it because it's understood that automatically this is going to be your first carbon. So this is carbon number 1. And I'll go clockwise just because I'm used to clocks, but if you want to go counterclockwise, it won't hurt anything. On the second carbon, we have a methyl group. On the fourth carbon, we also have a methyl group, which doesn't fit super nicely, but there we are. And structurally, there wouldn't be that much of a difference. Our pentanol, or our pentane, cyclopentane ring would look like that. And then we show the OH, and 2 and 4 get the methyl branches. And finally, propan 1, I don't like that E, but again, not a disaster that it's there. Propan-triol, so propane is 3 carbons. 1, 2, 3. Triol means we're attaching 3 hydroxyl groups, and there's 1 on every carbon. So OH, OH, OH. Do you have to alternate them like this? Absolutely not. I'm doing that because my understanding of VSEPR tells me that the bonding electrons here would repel each other, but that isn't critical to showing the structure at this point. Okay, so there's propan 1, 2, 3 triol, and structurally it would be 1 carbon, 2, 3, and then you show OH, OH, OH. These lines are fine because there's an OH on one end of them, and we understand that the endings here are the original carbon atoms. Fair enough. Next unit, we see a new functional group. It's called the either carboxylate or carboxyl group, depending what's attached to it. And that will show us how species like vinegar are made. So we'll see you there.